Start by adding a blink font flag to switch between the illumination models, the color of the directional light, the direction of the directional light, the spotlight color, the spotlight position, the direction and angle of the spotlight, the attenuation factors of the spotlight, the point light's color, the point light's position, the point light's attenuation factors, and the ambient light's color. Go to APP-CPP and add the cube update constants buffer. They use blink font flag, camera pause, ambient light color, directional light direction, directional light color, spotlight position, spotlight color, spotlight direction and angle, spotlight attenuation, point light color, point light position, and point light attenuation. Open vertex formats H and add a vertex post normal text called vertex type. Declare its position, its normal, and its texture coordinates. Open cube H. Declare shader constant struct and add the number of textures, use blink font, the material's specular exponent, the world view projection matrix, the world matrix, the eyes position, the ambient light's color, the direction of the directional light, the color of the directional light, the spotlight's position, the spotlight's color, the direction and angle of the spotlight, the attenuation factor of the spotlight, the point light's color, the point light's position, and the attenuation factors of the point light. Redefine vertex type as vertex post normal text chord and add the normal values to each vertex of the cube. Add a static convex per float with the specular material exponent as 1024. Redefine align constant buffer size as the size of shader constants. Change the rotation delta on the y-axis to 0.002. Change the translation delta of the y-axis to 0.002. Add a static convex per float as 0 for y offset. Add a static convex per for the translation delta of the z-axis. Add a static convex per float as 0 for a z offset. A z translation float to search the translation value of the z-axis. Update the parameters of the update constants buffer function, bold use blink font, xm vector eye pause, xm vector ambient light color, xm vector directional light direction, xm vector directional light color, xm vector spotlight position, xm vector spotlight color, xm vector spotlight direction and angle, xm vector spotlight attenuation, xm vector point light color, xm vector point light position, and xm vector point light attenuation. Copy update constants buffer method signature and replace the one in cube CPP. Add the translation delta on the z-axis. Declare the shader constants as constants. In the world matrix construction, add a y offset to the translation and make an oscillator on the z-axis and add z offset. And copy the next attributes to constants. Num textures as 2, use blink font, material specular exponent, world view projection, world as the transpose of the world matrix, eye pause, ambient light color, directional light direction, directional light color, spotlight position, spotlight color, spotlight direction and angle, spotlight attenuation, point light color, point light position, and point light attenuation. Replace the WUVP for constants in memcpi. Go to the initialize function, in the input layout declaration, add the vertex normal as a new input element desk. In the 0 parameter declaration of the root parameters, change visibility vertex to visibility all. Replace the text chord CSO shaders for lighting CSO. Go to the folder view. In shaders, add a new folder named constants. Add a file on it named lighting constants buffer H. Go back to the solution view. On the shaders filter, add a new constants filter. Add to it lighting constants buffer H. Declare a cbuffer constants buffer with register v0 with num textures, use blink font, material specular exponent, world view projection, world, eye pause, ambient light, directional light direction, directional light color, spotlight position, spotlight color, spotlight direction and angle, spotlight attenuation, point light color, point light position, and point light attenuation. Go to the folder view, add a new pixel shader named lighting HLSL, and another vertex shader named lighting HLSL. Include the shaders in their respective filters. in the lighting HLSL vertex shader, include lighting constants buffer H, declare a vertex shader input struct with a position, a normal, and UV texture coordinates, a pixel shader input struct with the rasterization position, a normal, the UV texture coordinates, a view direction vector, and a world pose vector. Declare the main function. Build the vertex position by multiplying the vertex position to the world view projection matrix. The normal, multiplying the normal of the vertex for a 3x3 matrix of the world. The world position, multiplying the vertex position to the world matrix. The view direction as the difference of the camera's position to the world coordinates of the pixel. Copy the texture coordinates, fill the output object, and return it. Go to the lighting HLSL pixel shader, include lighting constants buffer H, declare a texture 2D array without specifying a size using the register D0, a sampler state using register S0, the gamma as a static const float with value 2.2, the inverse gamma as a static const float of 1 over gamma. Copy the pixel shader from its declaration on the vertex shader lighting HLSL file. Declare the main function. Declare the texture colors, iterate over the textures in the primitive, and accumulate the RGB values of the textures using the sample function. Normalize the normal value, normalize view direction. To apply the directional lighting, get the directional light's direction as the negative of the directional light direction normalization. Calculate the directional light diffuse factor, saturating the dot product between the normal and this value. Declare the specular factor of the directional light as 0. If using Blin, use directional light reflect to calculate the reflection direction as the normalization of the reflect function between the negative of the directional light's direction and the normal. Use view.directional light to calculate the result between the dot product of view dir and the directional light reflect, and the light specular factor as the power of the saturation of view.directional light to the material specular exponent. If using Blin font, calculate in halfway directional light the halfway vector of the normalization of the sum of directional light vector and view dir. In normal.halfway directional, calculate the dot product between normal and halfway directional light, and the directional light specular factor as the power of the saturation of normal.halfway directional to the material specular exponent. To calculate the spotlight, use spotlight diff to calculate a vector from the pixel's position in world coordinates to the spotlight's position. Store the vector's direction in spotlight vector, but normalizing it. Get the spotlight's direction, normalizing the directions component, and get the spotlight diffuse contribution factor using the dot product of a spotlight vector with the spotlight direction vector. Declare a specular spotlight factor as 0. If the diffuse factor contribution is higher than the factor representing the angle of the spotlight, recalculate the factor decreasing the contribution with respect to the angle factor of the spotlight. Calculate the distance from the pixel to the spotlight, and calculate the attenuation of the spotlight with the distance. Multiply the directional light diffuse factor to the saturation of the dot product between the normal and minus a spotlight vector, and attenuate this factor with the distance. For the specular light, if you are using Blin, calculate the reflection vector between the spotlight vector and normal. Calculate the dot product between view dir and the reflection vector, and calculate the spotlight specular factor as the power of the saturation value of the dot product to the material specular exponent. If using Blin font, calculate the halfway vector, do a dot product between the normal and this halfway vector, and calculate the spotlight specular factor using the specular exponent of the material. If the light is outside the cone, the diffuse contribution of the spotlight is 0. To calculate the point light contribution, first calculate in point light diff the vector from the pixel world's position to the point light's position. Store in point light distance the distance between the 2 points. Store in point light distance attenuation the point light's attenuation calculation, the point light diffuse factor, saturating the dot product between the normal to the opposite normalization of point light diff, and dividing this to the point light distance attenuation. Declare the point light specular factor as 0. If using Blin, calculate in point light reflect the reflection of point light diff over the normal. view.pointLight as the dot product between viewDir and pointLight reflect, the pointLight specular factor as the power of view.pointLight to the material specular exponent. If using blink fun, calculate the halfway vector of the normalization of the inverse of pointLight if and viewDir, the dot product of the normal to the halfway vector, and the specular factor as the pointLight as the power of the dot product to the material specular exponent. Calculate the diffuse contribution of the directional light, the specular contribution of the directional light, the diffuse contribution of the spotlight, the specular contribution of the spotlight, the diffuse contribution of the point light, the specular contribution of the point light, and the ambient light contribution. Calculate the output color as the sum of the diffuse and ambient contributions. Saturate this color and multiply it by the texture color values. Add the specular contribution of the lights and return the color applying the gamma correction. Open the vertex shader properties. In the additional include directories, add shader constants. Assign the type of shader as vertex shader, the shader model as 6.1, set the output file as outdir shaders, vertex shaders, file name CSO. Open the pixel shader properties. In the additional include directories, add the shaders constants. Assign the type of the shader as pixel shader, the shader model as 6.1, enable the unbound descriptor tables, set the output file as outdir shaders, pixel shaders, file name CSO. Compile the solution, run the application. We can easily see a specular light and the diffuse point light. Go to cube H, increase the y-axis translation delta to 0.02, the y-axis rotation delta to 0.02, and the z-axis translation delta to 0.02. Launch the application again, and now we are able to see the spotlight and the omnidirectional light specular contribution. As some of the calculation results depends on the normal with respect to the camera's direction, keeping the cube spinning allows us to view the results periodically.